Okay. So hello guys. Welcome to another problem solving special maths academy. Obukume Ejaife here, and today we're looking at the second problem from the 2023 PAMO that was held in Rwanda, and it's a number theory problem. Today's problem. It says to find all positive integers m and n with no common divisors greater than one, such that m cube plus n cube divides m square plus 20mn plus n square. Right? That's our problem. Okay, so the first thing we want to going to zoom in a little. So the first thing we want to do is like write out the conditions we actually have. Okay, so we have that m cube plus, okay, so we have m cube plus n cube divides m square plus 20mn plus n square. So we have this is true. We know that that's vertical sign means divide. Then we also know that the GCD of m and n is 1. They said they have no common divisors greater than 1. So we know this is also true. We have this. So from this we know this m cube plus n cube, we can write it as, it can be factorized as m plus n into m square minus n plus n square. So if this divides m square, then it means that n plus n has to also divide like on this. So we're getting somewhere now. So this also means that n plus n has to divide this. Okay, let me do this. And this, and the m square minus mn plus n square also has to divide m square. Right, so far so good. So at this point I would say let's use some kind of mode techniques now. So I'm cleaning some of the top because take this out. And take all this, we don't need all these parts anymore. So let's come up here. Let's try something here. So we know that I can write, so this is like 1, we can call this 1 and 2, right? So from 1, we know that n plus n is, you know what modulo means, right? It's like equivalent to 0 in mode n plus n, right? So I can bring this here, so that this means that m is equivalent to minus n in mode n plus n. Then so that this so this m square plus 20mn plus n square is somehow equivalent to, so m square is equivalent to n square, right? Mn is to multiply this by, if m is equivalent to minus n, if I multiply both sides by n, we have mn equivalent to minus n square, right? So 20nm will be minus 20n square plus n square in mode n plus m. But to know n plus n divides this, if you come back here, you know n plus n, sorry, yeah, if you come back, okay, to 1, from 1, let me clean this arrow, from 1, so we know that from 1, n plus n divides this, n plus n divides m square plus 20mn plus n square. So this means that this has to be like equivalent to 0. This means the remainder is 0 in mode n plus n, right? So it means this is equals to 0. It means it's 0. And so okay, so if I do use that, so it means in place of this I'll put 0 now. So this is equals to 0. So it means that, and on this side is equivalent to n square plus n square is 2n square. 2n square minus 20n square is minus 18n square. So I have something like minus 18n square being equivalent to 0 in mode n plus m. And this means that if I divide through by the minus sign, that means n square, 18n square is congruent to 0 in mode n plus m, right? Okay, and so what can I still do with that? Okay, so I know that if the remainder is 0, if 18n square is equivalent to 0 in mode n plus m, then that means that n plus m has to like divide 18n square. That means n plus m is a factor of that. But we know that, so we can check the GCD of n plus m and 8n square is, you know that first of all, if we use this Euclidean algorithm for the GCD, so you don't really need that. Okay, let's come back to this later. Okay, let me just leave 2. Okay, let me just take out both. We can always write that out later. So if we use the Euclidean algorithm, that is like GCD of from Euclidean algorithm and n plus m and n is equals to GCD of n plus m minus n and n, right? Which is equals to GCD. This is from the Euclidean algorithm of m and n, which we already know as 1 from the problem statement. They have no common divisor greater than 1. So it means that these two things, n plus m and n, are relatively prime. So it means n square and n plus m have no common factors. So it means GCD of equals 1. That means you have no common factors. That means if n plus m divides 18n square, then it means that n plus m has to divide 18, since GCD of that n plus m and n square equals 1. So it means n plus m has to divide 18, and n and m are positive integers. So we also know that n plus m is greater than or equals to 2 and divides 18. So that means n plus m is going to be a member of this set, positive divisors of 18, which is greater than or equals to 2, 2, 3, 6, 9, and 18, right? So we know what n plus n is. Then this is where, so from 1, the first condition, from 1 we have all this information so far, which is like really helpful because now we can break cases down. So we'll now come to the second part of the problem, because we had 2 identities from the beginning, 1 and 2. So using 1, we'll be able to generate this. Okay, so let me write out the 2 in this we had earlier. We know that we had this. This was 1. So with 1 and this, we after working on this, we had this was true. So now we're going to work on 2, that is m square dividing this. So let's, before we like work on this, I want us to think about this. Like, we know that 3 divides 6, right? And we cannot, if we subtract 3 from 6, we also know that 3 divides 6 minus 3 as 3 divides 3. This is also true. This is true. If this is true, also true. So why? Because this was second one was true because 3 is a multiple of 3. So right. So if I subtract multiples of each other from inside, it should still divide. So I'm going to do something like that here. Since m squared minus mn plus n squared divides this, then this also implies that m squared minus mn plus n squared has to divide this minus this. And this is true because this m squared minus mn divides this, so this is also true. So this means that m squared minus mn plus n squared has to divide. Whatever I subtract, m squared minus m squared goes out. 20mn minus minus becomes 21mn. Then n squared minus n squared is 0. So that is just, we have this, that m squared minus mn plus n squared divides 21mn, right? So far so good. Then we can use this information now. We know that so now, like, check, if you check with the Euclidean algorithm, you see that GCD of m and m square minus mn plus n square will be equal to the GCD of m and n square. Why is this so? Because so m square, let me explain why this GCD stuff works like this. So this is like a multiple of, so we'll see that m divides this, m divides. So if at all there's going to be any other common factor to worry about, it will basically be what m and n square share together, which we already know that is 1 because m and n have nothing in common. So we have that the GCD of m and m square minus mn plus n square is equals to 1. Similarly, we also have that the GCD of n and m square minus mn plus n square is equals to 1. So this means that, so if I use this combined with the GCD arguments, then I'll have that m square minus mn plus n square has to divide 21. So that's what we have so far. So we have that has to divide 21. So we know that this is m square minus mn plus n square has to divide 21. Okay, divide 21. And this means that you can write this as we can write this as m plus n all squared minus 3mn has to divide 21, right? So far so good. So, and we know what m plus n is going to be like, so we just need to consider cases now. So from here on, it's going to be mainly an issue of casework. So let's just go into cases now. So now we have this dividing 21. That means m plus n all squared. So let's check. This is at least 4 when m and n are this, and this is greater than or equals to 4. Okay, so how do we proceed from here? So what I'm going to do now is try to like reduce the number of cases we have to check. So don't check too many cases. Let me clean all this out. We don't need all those parts. We've gotten what we need. Okay. So we know this. We have this, and this implies that, and we can write this as we already agreed on this. And this should be, so this is a positive divisor of this. This is positive, like you can see that this is positive. To check that, just know that if you want to check that this is positive, just use your AMGM. Although just know that m cube plus n cube is positive, so this has to also be positive, because this times this, since this times this is a positive number and this is positive, and m cube and n cube are positive, so it has to be greater than equals to 0, something like that. So with that, we can just know that this is a positive ISO of 21, and it means that n plus n all squared minus 3mn is going to be a member of this set. 1 3 positive ISOs of 21. Okay, 21 doesn't have too many cases to consider, so we'll just have this. So we're almost at the end now, so what we'll have to do now is just to take cases. So you now say, okay, so now it's come to at case work. So case 1, n plus n equals 2, right? Then we have that this is, if n plus n is 2, this is 2 square 4 minus 3mn. Then we have that 4 minus 3mn has to be like this. So we know this has to be like an integer, and this is going to be, if we reduce this, so let's check now. So if we reduce this case, this is kind of congruent to like 1 in mode 3, right? So it means that whatever 4 minus 3mn is going to be, when you divide it by 3, it has to be remainder than 1. So it means that using this, it means that 4 minus 3mn is either going to be equals to 1 or 7. So if we solve, this is like 3 equals 3mn, and mn equals 1, or minus 3 equals 3mn, and mn equals minus 1. This one will not work for obvious reasons, because mn is positive, so there are no solutions here. So usually basically when m plus n equals 2, the only things we have to worry about is mn equals 1, and we can see that mn, the only solution to this is 1 1, because 1 plus 1 is 2 and 1 times 1 is 1. So when m plus n equals 2, the only solution is 1 1. So we can, let's just like get a dedicated space at the left, okay, at the right rather, and list out the solutions to get. So we have mn equals 1 comma 1 as this for case 1 when m plus n is 2. So let's take out this case now, since we've already finalized what that case looks like. Let's go to case 2. So this is what casework is about. So case 2, m plus n equals 3. Then it means this is 9 minus 3mn. So we can also know that this has to be positive. So this has to be greater than 0, right? Because this is a positive IC of 21. That means minus 3mn has to be greater than minus 9. That means mn has to be less than or equals to 3. Wow. So this means that, what can we use here? So mn has to be less than or equals to 3, and keep this in mind. I also know that this has to divide 21, because now we're using m plus n equals 3 now. So we know that this has to divide 21, and if we divide both sides by 3, and this implies that 3 minus 3mn, okay, 3 minus mn has to divide 7. Okay, so we can check. So this is either 3 minus mn equals 1 or 3 minus mn equals 7. So here we have mn equals 2. Yeah, there are no solutions for this case either, so it is only mn equals 2 here. So yeah, because it has to be like, and this makes sense because 9 minus 3mn has to divide 21, so it's either going to be this, and it has to be a multiple of 3, so it's either 3 or 21, and checking, so only mn equals 2 works. So I hope this makes sense. So we have that this 9 minus 3mn divides 21. This is coming from this place, from here. While we plug n plus n as 3, we have 3 squared 9. Then 9 minus 3mn has to divide 21. They can divide both sides by 3, so you have 3 minus mn has to divide 7. And if you check, the only factors of 7 are 1 and 7, positive factors of 7. So it means 3 minus mn is either equals to 1 or 3 minus mn is 7. And this case will imply mn is negative, which is false. So it means mn has to be 2. So if we solve this case, you see that the only solutions here are 2 comma 1, or it's not too hard to see, or mn equals 1 comma 2. So these are the only things that can give you two positive integers, 2 plus 1 3, and they're relatively prime as well. So we have that also done. So we can move on to case 3 now. So let's go to case 3 now. So we've done for that. So case 3 is when m plus n equals 6. So when it equals 6, then this means that m will be equals to 6 square, which is 36 minus 3mn. And we know that this has to be on this set, because that is 1 3 7 or 21. And we can see that 3 divides this. So whatever this is going to be has to be a multiple of 3. So with that, we can easily see that it's either it's equals to this or it's equals to this. So if we check, this is 33 or 15. So we have mn here being 11 or mn being 5. Two positive integers I'm about to give you 11 is only 11 and 1, and 11 plus 1 is not 6. So there's no solutions for this case. So when mn equals 5, we know 5 times 1 is 5, and 5 plus 1 is 6. So that works fine. So 5 and 1 will also work. 5 1 or 1 and 5, and they are relatively prime, so that also checks out. So we've done 2 3 6, remaining just 2 more cases. Let's just still stay together. So you know why we are changing there 5 1 and 1 5, because they are not necessarily is like ordered pairs, so they have different meanings. They don't really change anything, but in the exam you can just put 5 1 and all the permutations, it still works fine, but over there you have to list them out explicitly like this. So we're at case 4 now. We're almost at the end. M plus n equals 9. So this means that m plus n all squared minus 3mn will be 9 squared minus 3mn, which is 81 minus 3mn. And this is dividing 21, and this is a multiple of 3 again, so it means that the only multiples of 3 which are divisors of 21, this is either 3 or 21. So you can check, so this can be 78. 81 minus 3, 78, and this implies that mn is 26, or this can be 60, and this means mn is 20. So this case means either mn is 213 or 13 2, whatever it is, the sum is 15, which does not equal 9, so no solutions for here. But in this one we have if you see 4 and 5, 4 plus 5 is 9, 4 times 5 is 20, and 4 plus 5 is 9. So this checks out, these two cases checks out. So this is mn, and the GCD is also 1 4 5 or 5 4. You can check that there are no other solutions that will give you 20. There's no other two numbers that you multiply to get 20 and add to give you 9. So those is the only solution for that case. So for case 4, and finally we can go to the last case now, which is the case 5. So case 5, m plus n equals 18. Then we have this, we know we are still using our initial identity. 18 square, which is 324, dividing 21. This is a multiple of 3, so anything divided has to be this. So it means that it's either equals to 3 or 21. So we have these two cases. So this means that this first one implies that, okay, let's see. Okay, let's come down. This implies that 321 is 3mn, and then that means mn is 107. I think this should be prime, so there are obviously no solutions here, right? Yes, it's prime, so there are no solutions there. So all this, or 324, and then we have 303. When you subtract and then you divide, mn is 101. This is also prime, so there are no solutions. So for the last case, there are no solutions for that case because two primes, they're already making this already too big. So we've come to the end of this video. So these are the only solutions: 1 1 2 1 1 2, 5 1 1 5 4 5, and 5 4. So these are the only solutions to this. So with that, there are how many set pairs? 1 2 3 4 5 6 7 pairs. And so with that, we've come to the end of this video. So you can see that it was actually a difficult problem. It was just mainly manipulating the given conditions to get the identities out, then doing the necessary casework, and everything fell apart later. So with that, we've come to the end of this video. It was nice having you guys, so stick around for more videos and interact with us on all our platforms. Goodbye for now.